The project that I want to talk to you about is substraTEE. It's a project that we do for the Web3 Foundation. So we are, like you, we are grant winners with the Web3 Foundation. The main goals that we want to tackle are the big challenges of blockchain, so to say. So confidentiality, scalability, interoperability, and we have a special way how we want to achieve that. We want to use trusted execution environments. So with the trusted execution environments, we have, of course, to trust the manufacturers. So in short, I will present what they are about, but we think it's a very quite production-ready approach to bringing confidentiality and integrity to off-chain computations. The state where we are at is we have delivered that first grant project, and we have a very simple demo with private token transfers. So you have a token maintained within a T, and you can have transactions where no one learns who is transacting how much with whom. So a T for, if I don't know if any one of you knows what a T is, then I can skip this. No, I'll keep it short. So what we are used to is that the administrator of the machine has access to everything. So the administrator can see memory of all the applications that are running, can change the code of the applications that are running, and the same applies to all the viruses, malware that gains administrator privileges. So that's what we're kind of used to, and what T's deliver is to have a hardware enclave within your CPU where this doesn't apply. So the administrator has no way to see what the program is doing. It only knows what the code of the program, and it sees some encrypted payload that enters into that service, but it doesn't know what the internal state of that program is. And so the same applies also to malware, except, of course, for the kind of malware that specifically targets T's. And one special thing about it, well, no, let me first tell you what the idea is. We have a blockchain. It's a Web3 project, so it's a substrate blockchain. And we implemented an off-chain worker. So the idea is that you invoke your call by means of a transaction on-chain, but that the transaction is actually executed off-chain. So we listen to events, to new requests, then we process them, and we send it back to the chain. And in a further stage, we could imagine that people interact directly with these workers. So we gain a second layer approach where we also achieve scalability, because not every transaction has to be on-chain. And now the important thing is the code that runs in the T is open source. So if we get a remote attestation from Intel SGX, in that case, we can convince all the users that this service here is running on a genuine hardware and is really running that code. So if we have deterministic fields, we know the hash of this binary that will run here, and Intel will give us an attestation that the hash of that binary which is running is indeed the one we think it is. Now, what we delivered as a demo is this private token transfer, and the way it works is we have a call like transfer such and such from Alice to Bob, and then we encrypt that call, the entire call, and supply it to the blockchain as a payload of another transaction. So that means we have an opaque call. The validator of this blockchain doesn't see anything. So it just forwards an event to our T. In the T, it gets decrypted, and then it enters the state transition function. And in that case, what is special about this is we actually instantiated the same logic which runs in substrate blockchains within the T. So we didn't come up with our own token contract. We took the same code that Parity wrote and instantiated it in a T. So here we have the whole token logic. And of course we need some state, and we don't use on-chain state. So we have our own state, which is encrypted with SGX functionality. And so the whole update, that the state, all the current balances are hidden, and all the state updates. Now we have the problem that if we only have one worker, that would be a very brittle design, because what happens if that worker is offline or even the hardware is dead? So we need redundancy, and in that case, we just have several workers processing every request in parallel, and they exchange their state over IPFS. But that's more of a bootstrapping approach. So if there is a worker already, it broadcasts its state to IPFS, and then as soon as the next worker registers, it bootstraps its own state from IPFS, but then just goes on by just listening to the same events, and they process everything in parallel. What I didn't say so far is the whole remote attestation. So if you join as a worker, you need to supply a remote attestation from Intel attestation service to the chain. The chain verifies the remote attestation and enters, writes a new entry to that registry. And as the state here is encrypted, we need also to have a key sharing between enclaves, because they want to access the same state. So what we do is mutual remote attestation. So the enclaves talk to each other until they are convinced that both are genuine, and then they exchange the keys.
So maybe before we move on, so basically the state is fully encrypted, so the workers don't see anything about the state because that's hidden. And there would still be, I guess, information leakage in terms of like transaction fails. So I learned that like this guy doesn't have a balance, so that's orthogonal of the privacy model.
I mean, what leaks is you need to use an account in order to supply the transaction. So it is public that you called some call of that off-chain worker, but all the payload is decrypted. But we didn't. I mean, the privacy model doesn't go into detail in terms of. We are not yet at the point where we can like avoid all the side channels, like execution time, or I mean all that stuff is not. We're not there yet.
And you said you do this mutual attestation to establish the key.
Yeah.
But then, if there's more than two workers, then how does it work? Do they have pairwise keys, or do we establish one big one?
It's one key for all of them.
Okay.
So far, because actually you just pick the first key which is registered, and you do a mutual remote attestation with that one, and that one will provision you with the keys.
Okay, makes sense.
And if that one is not available, then you pick the second one. So it's not. It's meant for, let's say, small sets of keys. So the the next evolution will be direct invocation. So right now we need several transactions. We need one to supply the call, and we need another one to confirm that the call has been processed. And if we want to achieve scalability, then we need direct invocation. And that's more just of a concept slide that hasn't been implemented yet. So the idea is that the requester talks directly to one of the T's which is registered, and they need some kind of protocol among them to make sure that all the calls get processed. And then the idea is that they process several calls, and then just the call receipt which they write to the blockchain is not one receipt per transaction, but just one Merkle root for an entire tree of transactions.
And not only they kind of need to reach consensus, right? Because not only do they all need to get all cases or all calls, but they also need to get them in order, right?
They need to get the same order, yes, because we want the state to stay synchronous.
And how do they share the keys exactly? So this is supported by the TE directly? That they
So
could use the same key, or
key sharing
kind of sharing?
I mean, it could work as before, so that just the first enclave generates new keys and shares it with the other ones.
Mm-hmm.
That could work, but here we could also have some group key agreement protocol or something, which is also like future work.
Okay.
Do that. And now it only supports Intel SGX, but the idea is, of course, to diversify, and that's where I think blockchain comes in very handy, because well, the animation is very incomplete. Let's say we have Intel SGX here, and I'm hoping for Keystone to be available soon, so an open source T implementation. And then we could have attestation from different manufacturers, but for the same state transition function. And then we would have, well, the diversification is of course only for integrity, because we can have consensus about what the output is, but it's not diversification in terms of confidentiality. Because it is enough for one of the manufacturers to fail for the entire state to leak. But that's kind of the deal that we're making if we use Teams. So the first 5 milestones have been achieved. I don't know, how are we in time? I would have a short demo video. Demo would be cool. Sure. Okay, so you see that it's actually working. Now I need to share the other window, I guess. All right, let me start again. So over here we start a substrate blockchain node, which is pretty much the standard substrate, but with an additional module providing this remote attestation register. So we start the node, and we started with Genesis, so it's the first block. Over here we start a worker, which will subscribe to the events. So at first we do some bootstrapping, giving the enclave some funds. Then we do remote attestation, we register the enclave, we subscribe to events, and now we're waiting for something to happen. And here we have the client, which generates 2 incognito public keys or key pairs and 2 public ones. And Alice will use the public one to supply the invocation call to the chain. And the incognito accounts, they will never be visible for anyone outside the enclave. Oh, the result was a bit quick. So what you see over here is Alice has 1 million tokens, Bob already has 100,000, and then we invoke an incognito transfer from Alice to Bob, and then you see the event which was received, which is processed, and if we query that state again after that, then 100,000 has gone from Alice to Bob. There is a little detail why Bob already has 100,000. That's because the enclave state is different than the chain state. We have started with Genesis here, but when I did the video, I forgot to clear the enclave state. So that's how you see that the substraTEE has its own state apart from the blockchain. So, you have questions?
Yeah, so yeah, I was going to ask exactly about what you mentioned last. So the enclave state being separate from the blockchain state. So in a way, it models a completely different token that has like how is it then really connected to the on-chain state? Like if I want to prove to someone on-chain that I have these tokens, that doesn't really make sense, right? Because then I would disclose how much I have. So
yeah.
So how would I use them on-chain?
What we didn't do is the bridging from blockchain tokens to enclave tokens. And we could do that with a 1-to-1 ratio just by special calls where you can kind of, like a shielding transfer with Zcash, where you move or you lock tokens in the enclave's account, and the enclave gives these tokens to you in the enclave state.
Yeah.
And then this way you can move between the two, but the enclave cannot access chain state. What you would have to do is, and that's another rather low-hanging fruit where we could go, is substrate also has this smart contract language Inc. That's another module which you can instantiate on-chain to have smart contracts, and it would be pretty straightforward for us, like we instantiated the balances module to instantiate the Inc module, and so you would have your own, the entire DApp logic would be in the T, and you don't need to access chain state anymore. So the chain is really just there as a registry of remotely attested workers.
Yeah, and then the other way of the bridge would be, because the chain state would be inside the T, then it would just kind of write out saying like I'm unlocking these tokens, let's say,
yeah. If
it got like a matching transaction, and then they would be kind of free on chain, because then
yes, because they actually the enclave has to maintain one kind of transparent account anyway, because it needs to supply or send confirmation transactions to the chain. So it already has an account which could hold all the locked collateral, and then release that collateral on request.
Yeah. Yeah.
So that would be the way.
So you are using now Intel SGX, right? And am I correct that those enclaves are just the memory regions, the RAM? They're like protected, so they cannot be accessed by other.
That's part of it. I mean, how I explained it is not technically correct. So it's not kind of a hardware enclave, kind of like a coprocessor. That's not how it works.
Because that's how it sounds in your description. While
yes, yes, but that's more of a kind of low entry explanation. In fact, what Intel did is adding some extra instructions to their instruction set to change the mode how memory is accessed and code is executed. I guess there are people here which know more about it than me.
But those are memory regions in RAM, basically.
Yes, they are in the same RAM, but they are the instruction set makes sure that on the way to access the memory, everything is encrypted.
Yeah, but sniffing RAM.
You can sniff RAM,
but
It's encrypted.
But it's encrypted, right?
It's encrypted.
So the all content is encrypted. Okay.
It's encrypted only inside the
CPU.
Yes.
Okay, thank you.
but what
My question is answered now.
okay? I mean, there have been attacks like Forshadow, for example, which are mitigated somehow now by Intel, but still, it's a very severe attack because you can. It was a side channel attack over the cache somehow, and they could break confidentiality and integrity because they could fake remote attestations. So it's kind of a complete showstopper.
In my train of thought, I was going more towards like performance and scalability.
Okay.
But,
Actually, performance is quite reasonable.
Okay.
We have done some tests. We would, like with this balance thing, we would achieve something in the thousands of transactions for sure, and we haven't optimized anything. So we have a lot of file I/O.
So you didn't have
this.
to like play with this to make it run. It
No,
just
no,
worked.
no.
Cool.
And actually, I think the performance cost of SGX is only that you can only do single threading. And then you lose a little bit of memory access time because it's all encrypted. But we're somewhere in the percent, in 10-20% or something.
Good for you, work.
If you compare it with a single core execution. So compared with smart contracts, it's like it's like very fast. More questions?
Otherwise, I will ask another one. So then, of course, the evil question to ask is, if you're talking to the workers directly, is that going to be feasible? Because it sounds like, I mean, as I was hinting at before, you kind of almost need a blockchain to figure out in which order the workers want to do the work. Are you really gaining something there if you're talking to the workers directly, or like, or how do you see this basically? Like, because of course it would be great if we could talk to them directly.
Yeah.
Both from like kind of the cost aspect and the performance aspect and scalability aspect, but like, are we really gaining anything there? Because it feels like we are we need a second blockchain to talk to the first one.
Well, there needs to be some consensus among the enclaves. I would claim that we don't need a blockchain, but we need a consensus protocol.
Yes.
But as a first guess, we could do something like a load balancing like we have it for cloud services, but not with the aim of really balancing load, but of just having some entry point which then selects which of the workers will do the work, and then you can do some kind of like we have with the Aura protocol, for example, that you just take rounds in who will do the next bunch of which is kind of not fully decentralized, because we have kind of one access point, one address to talk to, which does the dispatch. But if we get 1,000 times more transactions per second, then that might be worth it. And it's still not centralized in the sense you could still have failover services or kind of with respect to resilience, it's still quite decentralized.
Yeah.
Politically.
No, I understand that.
Yeah.
Connected to that, so kind of you have now two layers. You have basically these workers there doing some work. You said you need a consensus algorithm and everything. So, I mean, what blockchain has is also this incentive structure to do the work. That's also lacking on this side. So basically, I mean, you're providing CPU power, time, whatever. There's no incentive structure there. Basically, what happens here is you're doubling some stuff. Wouldn't it be just like more or easier to do to just merge this into the client somehow as a feature?
That's what we have been thinking about, so that we could kind of integrate the SGX enclave into the usual validator node. We could do that, but it's actually a bit more than is really necessary, I think. Because the way we do it here, we might not need that incentive model. Because if we say, if you want to run a DApp, then you need to run your own workers. So there is a blockchain, which is one global blockchain, which is Polkadot, for example, or a parachain of Polkadot. And then if you have a DApp with your smart contract, then you run your own workers. That doesn't work if the contracts need to interoperate, because then the states would be separate. But this way you could avoid having an incentive model, because the incentive would be for the DApp to survive.
Yeah, so sounds to me a little bit like, yeah, I mean, if I run a client for a blockchain, so if I want to be part of the blockchain, run the client, you don't need an incentive.
Yes, but I mean, if you develop a DApp,
but
you're a different, you're kind of a provider.
But still, the database needs to be synced.
Yeah, and of course it would. I mean, the playing devil's advocate, what people would directly say is that a lot of current dApps have the advantage that if the company behind them dies, they keep on going, right? Which
the same would apply here, because running a worker is unpermissioned.
If you can get the right state from IPFS, if you know where to get it, yeah.
Yes, and you can, because the IPFS hash will be written to the chain.
Okay.
So everyone knows where to get the latest state. So as long as there are people, stakeholders of that DApp, there will be workers, because they want to see that DApp working. But it's a different model than for in Ethereum. You have one chain, and if you register a smart contract, and it's out there, and it's different. It's a very different model, of course.
Is there an open hardware alternative to Intel SGX?
There is a Keystone, which is an academic initiative, and as far as I know, isn't Surjan having something? Or involved in something.
Yes.
I don't know who of his team, but I think they are working on some RISC-V. And Keystone also is a RISC-V architecture, but right now you can only run it with QEMU. So in the emulator, which is pointless. But even if we have an open source T, we would still have to trust the silicon fab, which produces it and supplies the attestation service. Because we need, for this, we really need remote attestation, because it's completely useless if we don't have that. And that's the problem with ARM Trust Zone. ARM Trust Zone is kind of a competitor to Intel SGX, but there is no way to get a reasonable remote attestation, because it's an IP core which is integrated by the Freescales and Texas Instruments and whatever. And these companies don't supply remote attestation. Not yet. But ARM Trust Zone is something we played with just unfortunately with no success in terms of remote attestation. Thanks very much. Yeah. Thank you for lunch. Yes, thanks for the presentation.